So in this video, we will apply the function analysis we've been learning up to this point to the kind of partial differential equations, or in fact, ordinary differential equations that we introduced in chapter 1 as a motivation for the theory. So let me remind you that we were looking at ODEs of this form, say second derivative in u plus a multiple of u equal to f for x, let's say in the interval 0, 1, interpreting in the weak sense, that is to say, meaning that the integral of u prime, or I should say, meaning that minus the integral of u of x times the second derivative of phi dx plus lambda times the integral of u of x against phi dx is equal to the integral of f of x times phi of x, and we want that to hold for every phi that is C infinity and compactly supported in the interval 0, 1. We could also be discussing boundary value of this together with this equation in its weak formulation, and you would have to interpret u of 0 and u of 1 through the continuous representative of u that you might get through Sobolev embedding. But let's not do that here. What I want to do here is see how we move from the L2 theory that we developed in chapter 1 to an LP theory, and how we move from a theory where, let's say, lambda is constant to a theory where we allow lambda to vary with x. So recall first that we've proven that for every f in L2 of 0, 1, there exists a unique u, which is going to be at least in H1 of 0, 1, and which is such that the equation holds weakly, so such that 1 holds. And we've also seen along the way that there exists a constant c such that for every f in L2 of 0, 1, that element u of H1 is in H1 norm smaller than a multiple of the L2 norm of the inhomogeneous term f. Now, our goal will be to get an extension of that to LP. So let me first introduce a little definition here. Given a p between 1 and infinity, I'm going to introduce the space W1p as being the set of all those functions f in LP for which there, so let's do that on 0, 1, LP of 0, 1, for which there exists a g in LP of 0, 1 such that the integral of f against phi prime on 0, 1 is equal to minus the integral of g against phi for every phi cc infinity of cc of 0, 1. So this is the Sobolev space with integrability exponent p. So W12 is the Sobolev space H1. And of course, we use the same norm. We use the norm defined in the following way. W1p norm raised to the power p is equals to the LP norm of f plus the LP norm of the weak derivative of f raised to the power p, where this g here that we obtain is what we're going to call, and it's going to be unique, is what we're going to call f prime by definition. Okay, so that extends the definition of Sobolev spaces as subspaces of L2 to subspaces of LP. And then we will also introduce the Sobolev W2p, which is the set of element f in W1p, for which, you guessed it, there exists a unique g, which we're going to call f second in LP of 0, 1, such that the integral of f prime phi prime, which makes sense because f prime is an element of LP, is equal to minus g phi for all of phi in cc infinity of 0, 1. And the norm that we have on the second order Sobolev space is again what you probably think it is, the LP norm of f raised to the power p plus the LP norm of its derivative, weak derivative, plus the LP norm of its second weak derivative, all of that raised to the power p. Okay, so having defined these spaces, what is it that I want to show? I want to show that for every f in LP, I want to show there exists a C such that for every f in LP, there exists a unique U in W1P such that the actually a unique U in W2P such that the W2P norm of U is smaller than a constant times the LP norm of f, and the equation holds weakly. That is to say that the integral of U second, which makes sense now as an element of LP, so with a minus sign, plus lambda times the integral of U times phi is equal to the integral of f times phi. All these integrals are on 0, 1 with respect to the Lebesgue measure. So this is our goal, and we want to do that, this is our first goal, and we want to do that for all p in the reflexive range at least, so p between 1 and infinity. Now notice that the uniqueness is for free once you have this inequality here, because this inequality tells you in particular that if f were to be 0, then u would have to be 0. So if you have two solutions, the difference of the two solutions will satisfy the equation with f replaced by 0, and therefore would have to be 0. So really this is a question of existence and continuous dependency on the data, if you want, or on the right-hand side f. So we're going to need to prove that, and so the first step is to actually do it for p equal 2 and show that we have a W22 control on the norm of our solution given by Lax-Milgram. So let's do that first. So let T be the bounded map in L2 such that for every f in L2 of 0, 1, we have that the integral of Tf prime against the phi plus lambda Tf against the phi is equal to the integral of f against the phi for all phi c infinity compactly supported. We know that such a bounded linear map exists from the L2 theory we've done so far. Now I'm claiming that this is enough to, sorry I forgot a prime here, that this is enough to guarantee that T of f is in W22 and control the W22 norm. Now why is that? That's something we somewhat discussed before, but that wasn't literally in the notes in chapter 1. What can I say about Tf prime tested against phi prime? I can say that this is equal to f minus lambda T of f tested against phi, right? That's for every phi. C infinity compactly supported. Now that is literally telling me that, because this holds for every phi that is compactly supported, that tells me that Tf prime prime exists. So Tf second exists as an element of L2, so put it in a different way. This means that Tf is in W22. And what can I say about the W22 norm of T of f? I can say that the W22 norm of T of f, or maybe let's just say the L2 norm of the Tf second, is smaller than the L2 norm of f minus lambda Tf, right? You get that from this equation, because if you have the equation for all phi compactly supported in C infinity, you can take a limit and use density of that set in L2 to get an estimate against all phi in L2, and then that gives this estimate here. Now this is certainly smaller than the L2 norm of f plus lambda times the L2 norm of T of f, but we know that T of f is a bounded linear map on L2, so this is smaller than 1 plus lambda times norm of T, all of that multiplied by the norm of f in L2. So we do have that T of f is in W22, and we do have that the W22 norm of T of f is controlled by a constant times the L2 norm of f. So this goal of ours, we certainly have already reached it when p equal 2, basically out of the theory in chapter 1. But now let's try to have it for other values of p. So we're going to start by considering, in step 1, we're going to consider an f that is C infinity and compactly supported, so it is in every LP space, and we are going to assume that p is above 2. Right, now let's try to prove an estimate about the norm of our solution in that situation. So what do we know about T of f? Now we know that T of f belongs to W12. So if T of f belongs to W12, by sub f embedding, it has a continuous representative. And the continuous representative is going to have a sup norm that is controlled by a constant independent of f times the L2 norm of f for some c independent of f by sub f embedding. And that was part of what we proved about sub f embedding. Okay, so we have a control of the sup norm of f, but then that means that the norm of T of f in LP, well, because it's LP of 0, 1, this is smaller than the sup norm of T of f, which is smaller than a constant times the L2 norm of f. But now p is greater than 2, so you can use Euler, just write that, right? This is c times the integral of f squared raised to the power 1/2. So you can use Euler with the exponent p over 2 and its dual exponent, and p over 2 is greater than 1 because p is greater than 2. And so Euler here tells me that this is smaller than the LP norm of f times the the dual exponent of p over 2, let's call that q prime, and then you take the integral of 1 between 0 and 1 to the power q prime, which only gives you a 1. Okay, so we have that for all f that is C infinitely and compactly supported. Now, the idea is that I want to get a W2P estimate for the norm of T of f in LP, and then I'm going to approximate any f in LP by C infinity compactly supported functions and get a solution in that way. Okay, so in the exact same way, we have that T of f is in W22, and so we can apply sub f embedding again for Tf prime, which is in W12, and we get that Tf prime infinity is smaller than a constant times the L2 norm of f, and so the same reasoning gives us the Tf prime in LP norm is smaller than a constant times the L2 norm of f, and then Euler tells us this is smaller than a constant times the LP norm of f. And then the reasoning also for the W2P condition tells us that Tf second, now understood as the weak derivative in, understood as an element of L2, if I integrate that against an f, so minus sign, I get the integral of f itself minus lambda t of f against a phi. So what does that tell me? That tells me that, because this is true for every phi, C infinity compactly supported, then I can take a limit and extend that to any phi in L prime, and that would be telling me that T of f second is an element of LP and has an LP norm controlled by the LP norm of f plus lambda times the LP norm of T of f. But we know that the LP norm of T of f is a constant times the LP norm of f, so this entire thing is smaller than 1 plus lambda times the constant we had in this line times the LP norm of f. Okay, so what have we proven? We've proven that for p above 2 and for f C infinity and compactly supported, we have a solution T of f that is in W2P. Now, how do we get from that to a solution for any f in LP? Well, we pass to a limit. So we have that there exists a C such that for all f, C infinitely compactly supported, there exists a U, and it's going to have to be unique, but right now let's just say there exists a U in W2P that satisfy norm of U in W2P is smaller than this constant times norm of f in LP, and U satisfy the equation in the sense that minus U secant phi plus lambda U phi is equal to integral of f phi. Right, but now what do? You say for Fn for f in LP, let Fn a sequence of function in C infinity compactly supported that converge to f in LP. Right. Now, for any Fn, there exists a Un in W2P that satisfies the equation. So I have that there exists a C such that for all n in n, there exists a Un in W2P such that Un in W2P is smaller than C times Fn in LP, and you satisfy the equation with Fn replacing F. Okay, but now Un forms a Cauchy sequence in LP in W2P, and W2P is complete. Well, we haven't quite shown that, but it follows from the completeness of LP. And so what we get is that Un has to converge to something. So there exists a U in W2P such that Un minus U in W2P norm tend to 0. Okay, and now what can I say about this U and the equation? Well, the integral of U secant n phi is going to tend to, it's a real number, to the integral of U secant phi for all phi in C infinity. That's because the strong convergence in LP implies the weak convergence in LP, right? You could test against any phi in LP prime, not just a phi C infinity compactly supported. Now, in the exact same way, the integral of U and phi converges to the integral of U phi, and the integral of f and phi converges to the integral of f phi. Therefore, what have we proven? So we have proven that there exists a C such that for every f in LP, there exists a unique U in W1P such that two things hold. First of all, the norm of U in 2P in W2P is smaller than C times the norm of f in LP, which again in particular means that this U has to be unique. That's for free after existence plus this norm estimate, and the equation holds weakly. Right, so we have managed to solve our problem in LP, but we've used the fact that we took P to be greater or equal to 2. Remember that this happened at this stage. Right? We had a control by the L2 norm of the inhomogeneous term, and I wanted a control by the LP norm of the inhomogeneous term, right? Such that the convergence to any f, such that I could handle any f in LP. But okay, this was somewhat easy because LP for P greater than 2 was actually a smaller space than L2. And the difficult case would be for P below 2, because then LP will be a larger space than L2. So let's see how we get the LP result for P between 1 and 2 from the LP result for P above 2. And you've guessed it, this is going to work by duality. So this is step 2. We are now going to assume that P is between 1 and 2. So let us do this duality argument. The first thing we need to realize is that the operator T that we can see as a bounded linear map on L2 is self-adjoint. as a bounded linear map on L2. Now, why is that? Well, if I take a u and a phi both C infinity compactly supported, and I look at T of u tested on phi, well, I can rewrite phi as minus T of phi second plus lambda T of phi, right? Because minus T phi second plus lambda T of phi is equal to phi, because T of phi is the solution to the equation with inhomogeneous right-hand side phi. Now, use the definition of weak derivatives, in fact, which corresponds to strong derivative by integration by parts in this case, and you get that this is minus Tu second applied to T of phi plus lambda T of u applied to T of phi, right? But, okay, minus Tu second plus lambda Tu is equal to u, because that's a T of u is a solution of the corresponding equation. So this entire thing is equal to u T of phi. That's for every u and phi compactly supported in C infinity, but because this set is dense, this implies that T is indeed self-adjoint. Okay, so T is self-adjoint, and I also know that it is bounded on Lp prime, right? Because P prime is above 2, and we've shown the boundedness of the map T, initially defined on C infinity compactly supported function, on Lp prime. That is to say that for every, say, u and phi both C infinity compactly supported, we have that the integral of T or u phi, it's a better way to put it, the absolute value of that is controlled by the absolute value, well, it's equal to the absolute value of the integral of u times T phi, and then you can apply Euler to that and control that by the Lp norm of u times the Lp prime norm of T phi, and we know that this is controlled by a constant times the Lp prime norm of T of phi, the constant being the norm of T as a bounded linear map on Lp prime. Now that's true for every u and every phi C infinity compactly supported. So what we have is that for every u C infinity compactly supported, the norm of T of u in Lp is controlled by a constant times the norm of u in Lp. But that means that T extends by density to a bounded linear map on Lp. Right, so therefore T extend to a bounded linear map on Lp. So we have the solution, at least if f, you start with an f C infinity compactly supported, you get a T of f, which is in L2, it's in Lp prime for all p prime, and now we know that T of f is also in Lp. Okay, so how are we going to use that? So we know that T of f is in Lp, and we also know by the equation that Tf second in Lp is going to be controlled by the Lp norm of f minus lambda T of f. And now we know that lambda T of f is in Lp, so this entire thing is controlled by 1 plus lambda times the norm of the operator T as a bounded linear map on Lp, which is exactly the same as the norm of the operator T as a bounded linear map in Lp prime by self-adjointness on L2 times the Lp prime of f. So therefore, Tf second is not just an element of W of L2, it's also an element of Lp. So we have that Tf second belongs to Lp, and we have this norm control. Now I claim that this is enough to show that Tf actually belongs to W2p, and that's because I can take a specific representative of the equivalence class of Tf prime and compute the Lp norm of that, show that it is in Lp, by saying that this is the Lp norm of the map x goes to integral from 0 to x of Tf second of y dy. and that's a representative of the equivalence class of TF prime. But now you can just use triangle inequality, control that by the integral from 0 to 1 of the LP norm of the map x goes to x goes to indicator function of the interval 0x, so 0y, sorry, yeah, my y is below x, so I want the indicator function of the interval 0x of y times tf second of y, right? Understood tf second understood as an element of L2. That's the LP norm of that, and then you do that dy. Now, I can use Hölder and control that by the LP norm of this integral in y, and so I get the integral from 0 to 1, the integral from 0 to 1, the indicator function 0x of y, the tf second of y raised to the power p, and then this is dx, and then this is dy. But you can control the indicator function by just 1, and an integral from 0 to 1 of something that doesn't depend on x is just 1, and so this entire thing is controlled by the LP norm of TF second. This is a form of what's called Poincaré inequality in that context. All right, but now we know that this is controlled by a constant C prime times the LP norm of F for some C prime independent of F. So you put all of these things together and you have that your solution is in W2P with the appropriate control, and that is true. Let's repeat the end of the argument. So there exists a C such that for every F, C infinity compactly supported, there exists a U in W2P such that U in W2P norm is controlled by a constant times the LP norm of F, and the equation holds. So U second minus U second phi plus lambda integral of U phi is equal to the integral of F phi for all phi C infinity compactly supported. And now approximating F in LP by Fn in C infinity compactly supported, we have the full result. We have that there exists a C such that for every F in LP, there exists a unique U in W2P. Again, uniqueness is guaranteed by the control of the norm, such that this holds. And here we've just used the fact that the equation holds weakly. We have a strong convergence of the solutions, the approximate solutions UN to the actual solution U, and strong convergence does indeed imply weak convergence. But what we're going to do next is something a little bit more subtle, where we really exploit weak convergence. So we're going to look at a more complicated problem. We're going to get a family of solutions that are uniformly in W2P, and then we're going to use reflexivity to extract a weakly converging subsequence that's going to converge to the solution of our problem. Okay, so let's use our LP theory to attack a more complicated problem. So let's look at the problem minus U second x plus lambda x U of x equal f of x, x in 0, 1. I'm going to have a p between 1 and infinity, and f in LP, and my lambda is going to be chosen as a continuous function on the closed interval 0, 1, say. So I'm allowing now the lambda to vary, but I don't want it to be 0 anywhere, so I'm going to assume that delta, there is a delta positive that is the minimum of the lambda x in 0, 1, and of course, well, this is smaller than the maximum of the lambda x, which I'm going to denote by m. lambda has to be bounded because it's continuous on a compact set. Right, so I'm going to try to have weak solutions of this problem. And the idea is that I'm going to construct approximate solution by considering a sequence lambda n of function of the form x goes to sum j equal 1 to some number capital N that depends on n times some numbers here. Let's take a approximation by lambda of xj times the indicator function of xj plus 1. Let's maybe close it on one side. Let's close it here for x for some mn, a natural number, 0, and xj, it starts at 0, and xj, a increasing sequence, so x0 is a number above 0, smaller than x1, up to xn, n plus 1, which would be smaller or equal to 1. So I consider a simple function approximation of my lambda. Now, by the theory that we have developed earlier, what have we got? We've got that for every n and for every j between 0 and nn, I'm going to have that there exists a c such that something happens. So there exists a c such that for every f in LP of 0, 1, there exists a unique u in W2P that satisfies norm of u in W2P smaller than c times the norm of f in LP, and the equation holds with lambda replaced by lambda n on xj plus 1. So this is W2P of xj plus 1, and then this is LP of xj plus 1. And so what I have here is that the integral of minus u secant phi plus the integral of lambda u phi, on this thing lambda is constant, so that's plus lambda of xj, it's the integral from xj to xj plus 1 of the integral of u phi xj to xj plus 1 is equal to the integral xj to xj plus 1 of f phi. Okay, this is equal for every j. Now, it's important here to realize that the constant we obtained before only depended on lambda. So really, should have been a bit more precise with that before, but the constant we are getting here is purely dependent on this number here, right, on the delta that we have here and the m that we have there. It only depends on the values of the lambda xj's that we have here. So the c can be chosen independent of any of the j's. And because we have that, and because this xj plus 1 from a partition of our interval 0, 1 may be missing finitely many points, but that doesn't change anything to any LP norm, what we have is that you can put these things together and you get that there exists a c such that for all n in n and for all f in LP, there exists a unique, I should have called that unj here, but there exists a un in W2P of 0, 1 that is such that the norm of un in W2P is smaller than c times the norm of f in LP of 0, 1, and minus u secant phi, which is 0 and 1, plus lambda n, sorry, plus the integral of lambda n u phi, which is 0 and 1, is equal to the integral from 0 to 1 of f phi. Again, that's for every phi. C infinity, compactly supported. Right, so we have a family of solutions that are solutions to a family of approximated problems, and they are uniformly bounded in W2P. So now assume for a second that we knew that W2P is reflexive. We'll prove that in a second. That's very easy to prove. It's just because this turns out to be a closed subspace of LP, and we know that LP is reflexive. So assume that W2P is reflexive. Okay, then there exists a subsequence U and K in W2P, right, that converges. And there exists a U in W2P such that U and K converges weakly to U. And that comes out of the boundedness of the sequence UN and the reflexivity of W2P. Okay, but U and K converges weakly to U, and lambda n converges almost everywhere to lambda. So by continuity of lambda. So what have we got? We've got that the integral of lambda and k u and k phi from 0 to 1 will tend, as k tends to infinity, to the integral from 0 to 1 of lambda u phi. Okay, but that tells me something about the u and k second. So the u and k second, they also have to converge to something. So u and k second, it's an element of LP, it's uniformly bounded, so it has to converge weakly to something that I'm going to call V. And so what I get is that minus integral of V phi from 0 to 1 plus the integral of lambda u phi from 0 to 1 is equal to the integral from 0 to 1 of f phi. Okay, so I claim that if I have a sequence that converges weakly in W2P, then the sequence of its second weak derivative converges weakly to U second in LP. Now, why is that? Well, let's have a look. So if we have the integral of U and K second phi, right, for any phi, say C infinity compactly supported, this tends to, as K tends to infinity by weak convergence of this thing in LP, to the integral of V phi. But in the meantime, the integral of U and K phi tends to the integral of U phi, phi second, right? And so this tells us that this V here has to be the second derivative of U. And because if U, I know that U is in W2P, so this has to be equal to the integral of U second phi. So integral of V phi is equal to integral of U second phi for every phi, therefore U second has to be equal to V. And that gives me the equation. That gives me that minus U second phi plus lambda u phi, and remember that lambda is a continuous function, not a constant, is equal to the integral from 0 to 1 of f phi. Okay, and that completes the proof, except that we haven't shown one thing. We haven't shown that W2P is indeed reflexive, so we're going to do that now. But what we've seen here is a very quintessential example of the use of Banach-Alao glue and weak compactness in PD applications. So what you do is you approximate your problems by problems you can already solve, But not only you can solve them, but you can solve them with a quantitative estimate. You know that the sequence of solutions to your approximating problem is going to be uniformly bounded in some sort of norm. And so because it's uniformly bounded, it has a weakly converging subsequence. And because the formulation of the PD is a weak formulation, it talks to the weak convergence. Weak convergence of approximated solution implies that the weak limit is a weak solution of the equation you started with. So this is very typical of the use of weak topologies to solve more complicated PD problems. And we could go further. We could replace the second derivative by a differential operator that also has varying coefficients. We could start making the problem nonlinear by making f, or semi-linear, that's what it's called. Making f depends on the solutions, and we will be able to run all sort of approximation arguments based on the extraction of weakly converging subsequence and the fact that our notion of solution is a weak notion anyway, so it passes to weak limits. Okay, now last thing we need to show, W2P, let's call that a proposition, W2P 01 is indeed reflexive. Let's do that now. So we consider the map J that goes from W2P to the sum of 3 copies of LP of 0, 1 and sends the function U to the triple U, U prime, U second, where the norm of a triple UVW in this LP plus LP plus LP space is by definition, if I raise it to the power p, say the LP norm of U raised to the p plus the LP norm of V raised to the p plus the LP norm of W raised to the p. So the norm of J of U in LP plus LP plus LP is really the same thing as the norm of U in W2P. So J is an isometry between a Banach space and a subspace of some space, which is LP plus LP plus LP. So we have that the result will follow if we can show that LP plus LP plus LP is reflexive. So it suffices to show that LP plus LP plus LP is reflexive, because then W2P will be isometric actually to a closed subspace of a reflexive space, and closed subspaces of reflexive spaces are reflexive. Now, why is LP plus LP plus LP reflexive? Well, you can consider the map that goes from LP plus LP plus LP of 0, 1 into LP of 0, 1 cube. And what you do is you take a triple UVW and you associate to that the map that sends x, y, and z to U of x plus V of y plus W of z. Right. And now I'm claiming that this map is an isomorphism. And I'll leave that as an exercise. T is an isomorphism of Banach spaces. I'm not claiming it's isometric, but just an isomorphism of Banach spaces. When you compute the LP norm of this thing, this is actually quite easily controlled by the sum of the LP norm of U, V, and W, and this map is obviously linear. And so what we have now is that you have an isomorphism between two spaces, one that we already know is reflexive and another one, and therefore the other one is also reflexive. So this is reflexive. And that concludes the proof, because we've identified W2P isometrically with a closed subspace of that reflexive Banach space.